Angela was asking for possible topics for the series. I happen to be doing a bit of work in this area, so I, without giving it a lot of thought, said, well, how about this topic? And I did say to her, well, it's perhaps a little bit recherche for what she had in mind for the series, but she didn't bat an eyelid, or at least I didn't see her batting an eyelid, and it appeared on the programme. So I'm going to talk about the idea of risk scores, and particularly in a social science context. And it's a topic, as we'll see, that's perhaps better used and understood in a more medical context, but I think it has some applications in a social science context as well. And what I might have done was actually given it an even more esoteric title of what are receiver operating characteristic curves, but I won't. I won't focus. Well, you might. A few people might have come just out of curiosity, but anyway, although I'm not going to talk explicitly about such things, I am going to, towards the end of the talk, I am going to just introduce them as an idea for integrating a few different ways of thinking about things. And I might have actually given it a much more general title, which is what is longitudinal data analysis, because what I'm actually going to talk about does usually involve the use of longitudinal data. Not absolutely necessarily, but usually when we're thinking about these kinds of problems, we need longitudinal data to try to answer them. On the other hand, of course, longitudinal data analysis is an enormously broad topic, and it wouldn't really make sense to have just an hour's lecture on that broad topic, because it includes all kinds of things, including at least one topic which has already been covered, I know, in this series, which is event history analysis. So what I'm going to say does relate to the way in which we think about longitudinal data, but it's clearly a subset of a much broader topic. So using risk scores is really a way of helping us to make decisions in conditions of uncertainty. That's the way I see the value of this method. And some people would actually think of them not so much as risk scores, but as statistical prediction rules. That is a phrase that you'll see in the literature. But I don't like particularly this idea of it being a rule. I think it's a help, it's a guide to making decisions, but it's not a rule for making decisions in that sense, because there are all kinds of other things that you would want to take into account in any particular situation. But it's a help, it's an aid to making decisions where you just don't know all the variables that you would like to know, which is a very common situation in social science and in statistical modelling, if you like. So that's, in essence, what we're thinking about here. And to put a bit of flesh on that, let's think of a few examples. So suppose we're interested in designing an intervention for young children and families in order to reduce their subsequent educational disadvantage. And we're wondering really who should receive this intervention. So we're thinking about something that happens at a particular point in time, which will have consequences for some later point in time. And for those of you who are a little bit familiar with sort of social policy in this country since the Labour government came to power in 1997, you'll know that this way of thinking has been quite important in their social policy. So, for example, they've introduced programs like Sure Start, where the aim is to try to address problems of disadvantage in families and in areas in order for there to be a payoff in the future. And the difficult issue here is to know who would benefit from this intervention. In other words, how should such an intervention be targeted? Because clearly, in the great majority of families, children will do well at school, they'll get educational qualifications, and there's no particular need for anyone to intervene to make that process possible. But there are some families where, at least in principle, you feel you could intervene to do something about it. And the question is really, who are those families? And one way of dealing with the issue, which is actually the way that most of the policies have been put into practice, is to say, well, we'll take a particular area and we'll focus our resources on this particular area. But that isn't necessarily going to be the most efficient way of doing things. And so we need some understanding of what the relationship is between early disadvantage and later education outcomes in order for us to be able to perhaps make some rational decisions about where to allocate resources. So that's one example of the kind of situation we're talking about. Let's think of another example, a very different kind of example. And this is really to do with methods. When we're doing longitudinal studies, we're concerned with the ways in which we do them, and in particular, the problem of the fact that people are lost from longitudinal studies as these studies continue. And the people who are lost tend not to be the same as the people who stay. So this introduces potential bias into our studies. And the question is, how might we reduce that problem? How might we lessen the bias that's introduced by attrition? And how we might think about the organisation of fieldwork resources. In other words, could we direct resources at those respondents who we think are more likely to drop out, in order that they are then, by getting, for example, a more experienced interviewer, maybe you would give an incentive. There are various ways in which you might intervene to lessen the problem of attrition in longitudinal study. And the question, again, is, okay, if you think that that would be a good idea, how should you allocate those resources? What should be the decision that you make in order to allocate those resources most efficiently? In other words, can we predict in advance who the people who are going to drop out are going to be, and then direct resources to them? So that's a second example. And a third example is one that I was at a meeting that actually chaired a meeting that was organised by the Social Statistics section of the Royal Statistical Society a couple of weeks ago, where we were thinking about statistical issues in child protection. And one of the talks was about, again, the issue of how social workers, faced with a range of families who they feel they need to intervene with, and not knowing exactly who they should give most attention to, in conditions of uncertainty. And the meeting was partly generated by the various tragedies and scandals, or supposed scandals, that there have been in this area recently. And again, the question is how best to try to deal with the scarcity of resources in order to try to allocate your resources most efficiently, to try to prevent neglect and abuse. And it was quite interesting to hear the reaction of the people who were at this meeting. Some people recognizing that this kind of approach of using this score would be appropriate, others very much opposed to the idea that you could make decisions in this way. There's a real debate to be had. In terms of the history of these ideas, they go back to work in signal detection, signal detectability in the 1950s. This is where the ideas were first generated, really. And this is, I'm not at all familiar with electrical engineering, but basically what people were concerned with at that time was that they were observing varying voltage. So they were looking at what was happening with the electrical current, and they were seeing spikes and troughs, and they wanted to distinguish what was a signal from what was noise. And that's really where the initial ideas for thinking about how one can make decisions on the basis of evidence in this kind of situations of uncertainty. That's where many of the ideas come from, and that article by Gleason et al. Appears in a sort of monograph in sort of Transactions of Electrical Engineering or something like that. I think it might be on the list I'll show you here. And then since then, the ideas have been applied very widely in epidemiology, as I said at the beginning, but much less so in social science. So a well-known example in medicine, probably the best-known example, is work which came out of what's known as the Framingham Heart Study. Framingham is a reasonably small town in Massachusetts, which was the site of an intensive study of heart disease. And what came out, one of the things that came out of that study was to generate a score that would predict whether or not someone would have coronary heart disease or not. And they used different variables which, on the basis of theory and empirical investigation, they knew would be predictive of someone having some kind of heart disease, diabetes, age, of course. As we get older, you're more at risk. Smoking, as we know, it's not good for you. Blood pressure, and cholesterol levels are all implicated in whether or not someone will have a heart attack in the future. But you could have all of those and not have a heart attack. In other words, there's no certainty of prediction from this set of variables, which are sometimes called risk factors, although I don't actually like that word very much, that phrase. But the relationship between those variables and the outcome is more than you would expect by chance, but is not, of course, perfect. And again, the decision that a doctor would then have to make is at what point should I intervene to prevent someone having heart problems in the future. There aren't so many examples in social science, or at least not as far as I'm aware. Probably those that are most well known are those from criminology, where people have tried to predict recidivism, in other words, the probability of reoffending having had some sort of custodial sentence. Or, again, rather similar to the child protection example, where they need to allocate scarce resources in terms of probation officers. And this is I'll give you this reference at the end, but this is an example, very interesting paper, where the problem was that probation officer resources were very scarce. This is in the US, and the question was, how should probation officers allocate their time in order to prevent people on probation then going on to commit murder? And again, showing how, in fact, it was possible to allocate resources more efficiently. So these are the kinds of questions that we need to think about. How likely is it that a person with a set of socio-medical characteristics will have a heart attack, and what are the implications of treatment? How likely is it that a person will commit a crime after leaving prison? How likely is it that someone on probation will commit murder? These are the sorts of things that we are trying to understand. In other words, we want to be able to model these probabilities, these outcomes, in order to be able to say, well, on the basis of this evidence, this is what we would predict would happen. And if we can do that well, then we have reasons for intervention. If we can't do it well, then we might well do better to leave the whole thing alone rather than trying to do something. So that's the background. That's why we're interested in these kinds of problems. And what I'm going to do now is to just go through an example, just to show you how it works in a very simplistic way. So the example is simplistic, and I'm going to do a couple kinds of corners, but just to give you a sense of how one would actually go about doing this kind of thing, and how you would possibly make decisions on the basis of the evidence that you've got in front of you. So we're going to assume that we've got a binary outcome. So in the medical context, whether or not you have a disease, for example, in the social science context, whether or not you reoffend, in the example I gave earlier, whether or not you drop out of a longitudinal study, all of these things are binary outcomes. And we've got a set of variables that predict this outcome, which we call risk variables. And I prefer to use the phrase risk variables rather than risk factors, because risk factor implies that you're talking about either having the factor or not having the factor. So in other words, there's a impetus to treat these predictive variables as binary variables as well, which actually I think wastes information. So I think it's better to think of them as risk variables and not to feel you have to compromise them. Now, if we've got this information, then we can estimate a function that relates the probability of a good or a poor outcome to the risk variables. Now, you could do this in a lot of different ways, and how you do it isn't really that important. You could, for those of you who know a little bit about statistical modelling, you'll say, that's a logistic regression. Fine. Those of you perhaps from a slightly different background, particularly if you're from the economics field, you say, that's a progress regression. It's fine, it's perfectly all right. You might, if you came from computer science, say, that's a data mining problem. In other words, you wouldn't necessarily set it up as a statistical problem, you'd set it up as a data mining. It doesn't actually really matter that much how you do it. The point is that you're trying to estimate some sort of function. And the question is, how accurate is this function? And the accuracy question is a question about not only predicting the disease, I'm using disease in a sort of rather generic sense, not only predicting the disease, but also in predicting the not disease. And that's a slightly different way of thinking about analysis from the way that we're usually thinking about predicting binary data. Because when we're usually doing this, particularly in a statistical framework, we're treating the binary outcome as if it's in some sense symmetric. We're not really distinguishing between the 0 cases and the 1 cases. We're just trying to predict that outcome. And we might use some sort of fancy measures of fit. Those of you who know a little bit about this will think, that's a pseudo spread or something like that. But that's not really addressing the problem that we need to address here, which is that we're interested in predicting not only the disease, but also the not disease, and we're not necessarily going to treat those symmetrically, because they have different implications. So we've got, as I suggest here, possibly a rather different way of thinking about the ways in which we approach the analysis of longitudinal data for certain kinds of questions. Clearly going to apply to all questions, but for certain kinds of questions. So we've got a function, which is our risk score. That's what the risk score is. And we then need to make a decision about where we're going to cut off this function in terms of how best our predictions are going to be put into practice. I'll come back to that point of where we put the cut-off point in a moment. But for now, basically we've got this function. And so to illustrate it, with, again, a very simple example. Suppose we've got 3 predictors of a binary outcome. And let's suppose that x1 and x2 can have 3 values, and x3 just has 2 values. So x3 is a binary variable, and x1 and x2 are both categorical variables. But this is for illustration, and there is absolutely no reason why all or some of these predictors there's no reason why they couldn't be continuous. They could have any distribution you like, basically, but it's just really to illustrate the ideas. I've chosen these categorical variables. And we call the probability of our poor outcome capital Q.
And we're saying that this probability of a poor outcome increases as each of these risk variables increase. So in other words, you're more at risk if your value of x1 or x2 or x3 is higher. And we're going to assume that the function that limits them is this function which we might have estimated using logistic regression. So we're just going to say that on the left-hand side, we've got the logit of p, and this is our function. So it's minus 3 plus 0.5 x1 plus 2x2 plus 0.5. But it doesn't particularly matter whether we use the logit or anything else, really. And from that, we can generate some predicted probabilities. So we can say that somebody who scores the lowest points on x1 and x2 and scores 0 on x3 has a predicted probability of a poor outcome of 0.38. And you can do that yourselves. You can just plug in the values into this function, and then you can go from the logit to the probability scale, and that will give you a value of 0.38, or at least I hope it will, unless I've made a mistake in the arithmetic. And then at the other end, if you're at the highest value for each of these values of the predictor variables, the predicted probability of a poor outcome is 0.99. So in other words, if you have the top values, the least satisfactory, if you like, situations, then you're predicted to have a poor outcome. But it does vary a lot according to the values of these satisfactory variables. And we need to think about how can we use this information? What are the implications of this information in terms of decisions that we might want to make? So suppose that we take our cutoff as a predicted probability of 0.9. What would that mean? It would mean that most of the cases that are defined in this way will have the poor outcome. But there's a risk that many of those who have the poor outcome are actually going to be missed. So by setting our threshold, which is our cutoff point, rather high, we're going to miss cases with the poor outcome. If we lower the cutoff, we're going to miss fewer cases, but we're going to include more cases with the good outcomes. In other words, we're going to treat cases that we wouldn't have needed to treat in the first place because they would have been fine. So we wouldn't have needed to have intervened. So in other words, there's a choice that we need to somehow rationalize this choice as to where this cutoff should be on the function that we're interested in. And what we can do is that we can construct what's often thought of as a truth table. And we can do this for any cutoff point. So what we've got is an outcome, either a poor outcome or a good outcome. And I mean, the poor outcomes are the ones, in the sense that we're interested in. And we've constructed our test, or if you like, our risk score, and we've decided where the threshold is. So we've chosen the threshold. So some people are below the threshold on the test, and others are above the threshold. And we have a number of people, little a, in this cell, who are predicted to have a poor outcome, who do have a poor outcome. In other words, we've got a sample where we do actually know what the outcomes are. Although we're interested in predicting people whose outcomes we don't know, we start with a sample where we do actually know the outcome. So we know that they had a poor outcome, but they were below the threshold. So they're mistakes, if you like. That group here are the people where we made a mistake. If we go down, those who have a good outcome and below the threshold, that's what we want. So we want A to be small and C to be large. And similarly here, B, that's a good thing. They have a poor outcome and they score above the threshold. But D, those with a good outcome above the threshold, again, are mistakes. So we need a way of summarizing that information. And one way we can do it is to talk in terms of the true and the false positive fractions. So the true positive fraction are those above the threshold who have a poor outcome divided by the total number with a poor outcome, b over a plus b. And of course we'd like that to be as close to 1 as possible, which means we'd like a to be very small. And we often call that the sensitivity of the test, or the sensitivity of the risk score. But we also have the false positive fraction. These cases, who score above the threshold but actually have a good outcome, divided by the total number of good outcomes. And if we subtract that false positive fraction from 1, we have what's often called the specificity of the test. So we've got these two situations, that the test, the sensitivity of the test, in other words, the extent to which we really do pick up the cases with our risk score, and the specificity, which is the the complement of the situation where we make mistakes in terms of false positives. So we can see that without some numbers. So if you look at the first table there, we've got 100 cases. We've got an outcome where the probability or the proportion of the poor outcomes is 20%. And we've determined the threshold such that half are below and half above the threshold. And in that case, the true positive fraction is 0.75, 15 over 20, and the false positive fraction is 35 over 80, or 0.44. But that's for a particular choice that we've made of the threshold. We might change that threshold so that instead of having 50 people above it, we only have 20 people above it. In other words, we make it a tighter criteria. We don't admit to so many people scoring above the threshold. What happens, we change the true positive fraction from 0.75 down to 0.5. This is a bad thing, but the false positive fraction goes from 0.44 to 0.13, which is a good thing. And we could do that over and over again. For any possible value that we could think of for the threshold, and if you think of these as continuous variables, then the threshold can vary continuously. So how do we represent this information? How do we represent these different kinds of cutoff points and these different probabilities of making mistakes? And this is where we see something which is a receiver operating characteristic. This is how we can summarize our accuracy. And what we do is that we plot the sensitivity, or the true positive fraction, against 1 minus the specificity, or the false positive fraction. And we do that for every possible cutoff point on the risk score. And so what we would hope to observe is something that is better in terms of being above this diagonal line, because this diagonal line is equivalent to tossing a coin. The diagonal line is saying, I will decide by tossing a coin. In other words, I have no more information than that I can get from just choosing by chance. That's what you would observe in terms of the way these change. This is clearly better than tossing a coin, but it's not perfect. If it were perfect, it would go up like that, across there and along there. And that would be where we don't make any mistakes at all. But we know that we're dealing with situations of uncertainty. So this is a representation of how sensitivity and 1 minus specificity change as we change the cutoff. Which is fine, and is a nice diagrammatic representation of it, but we need a summary measure of some kind. In other words, we need to be able to report, when we're discussing our findings, we need to, in some sense, report a summary of that curve. And the way in which is usually done is either talking about the area under the curve, The disadvantage of talking about the area under the curve is that it varies from 0.5 to 1. And it's not such a nice range, really. So what people usually do is that they transform the area under the curve to what they call a Gini coefficient, which is twice times the area under the curve minus 1, and that varies from 0 to 1. So in this particular case, the area under the curve is probably something like 0.7, so the Gini coefficient is about 0.4. But clearly you can have all kinds of different curves with different summaries. So that gives us a summary of the effectiveness of our risk score. In other words, if our risk score is effective, then we're going to have values of area under the curve close to 1, and also the Gini coefficient is going to be close to 1. That will tell us, if it's close to 1, that we're actually very much able to predict not only the cases, but also the uncases, the not cases. So not only do we predict the diseases, but we predict the not diseases as well. And that's fine, but that only takes us so far. And the other thing that we have to bear in mind when we're trying to use this idea of risk score, the risk score approach, is what are the costs and benefits of making mistakes? And how are we going to assess whether the threshold should be at this point or at that point? In other words, does it matter if we set the threshold high and we list some cases? Does it matter if we set the threshold low and we include cases that actually we didn't need to include in terms of outcome? And clearly that decision must depend on the costs of making a mistake. Then we get into lots of other literature, and I'm going to have to skip lots of things that one would try to cover if it were a sort of course in this kind of topic. But we've got the point of how we should determine the cutoff point, and we need to be able to assess the costs and benefits of the decisions. And it turns out that the optimal cutoff point is defined in that way. And the optimal cutoff point is actually related to the slope of the receiver operating characteristic curve. And it turns out to be k times this value of r. So that's the optimum value of the slope. And k is the odds of a good outcome. And that's usually more than 1, because we're normally talking about outcomes which are relatively uncommon. And R, capital R, is the ratio of the costs of intervening when a good outcome would have occurred. In other words, you treat cases that didn't need to be treated, it's a cost. So the net cost of intervening to prevent a poor outcome. In other words, how much does it actually cost to intervene? How much does it cost to set up short stop? How much does it cost to reallocate interviewers in a longitudinal study? So that's how we determine the optimum point on the receiver operating characteristics. So in other words, if we go back to a curve, we're talking about the slope, so we're imagining the tangent of this curve all the way along. So you can see that the tangent here, the slope is much greater, which is up here. So the slope goes down as you move away from this origin. The value of R is going to depend partly on the efficacy of the intervention. It's going to be substantially less than 1 for effective interventions, where the benefits exceed the cost, but substantially greater than 1 for ineffective ones. So the optimum slope is going to be smaller for effective interventions than it will be for ineffective interventions. And what the implications of this are is that if you have a relatively ineffective intervention, in other words, one that which you might have So there's a sense in which you have determined the effectiveness of the intervention, perhaps by some sort of randomized controlled trial. But it will be targeted only at those few cases with a high probability of a poor outcome. In other words, where the slope of the receiver operating characteristic is high, and the sensitivity is low, but the specificity is high. Whereas if you know that you have an effective intervention, then you're going to make that available to many more cases with consequent higher sensitivity and lower specificity. Now, there's a lot here going on in the background, which I haven't got time to go into. The important thing really here is, in terms of just getting a little bit of understanding about what these things are all about, is to think in terms of the kinds of mistakes that you can make, the extent to which you can understand that you've got some knowledge about the costs of making a mistake, and also the costs of intervening, and also the benefits. I mean, in the sense I'm just talking about cost, but benefits are a negative cost, if you like. So cost is a net cost. So if you've got all that kind of information, then you're in a position where you can actually say, this is where I think my cut-off point should be on my risk score in order to maximize the efficiency of the way in which we use our resources. And that's really what this is all about. It's thinking about using data in order to make effective decisions. And it's not, I think, a very common way of thinking about data. I think there are many situations where this could be applied much more widely. So I'll just very quickly mention places where you might read a little bit more about it. There are a couple of books, Krzyżanowski in Hand and Pepe, which are these two. The Pepe book is very much, it's called The Statistical Evaluation of Medical Tests for Classification and Prediction, very much aimed at epidemiologists, but has a lot of very useful background information. This is a very recent book that's come out, ROC Curves for Continuous Data. And again, it goes into a lot of detail about how you can use these ideas. Again, unfortunately, and not surprisingly, there's not a lot that's social science based. And if you do happen to look at this book in the library, you will see that on the spine there is a rather horrendous misspelling. So if you buy the book, you actually might ask for your money back because it's clearly misspelled on the spine. But anyway, that's a small point. And then there are some articles. This is the article I mentioned before about predicting on the basis of observed data, predicting who on probation parolees are most likely to commit murder and how one should deal with that. That's in the Journal of the Royal Society, Series A. Very nice paper, I think. This is a publication from the Home Office Research Unit, talking about how we might use these ideas for predicting reoffending. This is a paper, working paper that I've written, which is on the CCSR working paper. It's in that series and on the CCSR site. This is an article in the psychological literature, which I think goes into quite a lot of these issues in a lot of detail. It's well worth looking at if you're interested in these ideas. And this is the reference for the Framingham study, for the generation of the Framingham risk score for predicting heart disease. So there are various things that you might think you might like to look at in terms of taking this further. And I'll stop there.